operations in Naval Petroleum Reserve Number 4, a variety of construction projects take place. A number of natural factors, generally peculiar to the far north, influence all construction in PET 4. For 73 days, from mid-November to late January, there is no daylight, just 2 to 4 hours daily of gray twilight. Then there is temperature. During winter months, the mercury may drop to a low of 57 below zero. By midsummer, the temperature may hit a high of 78 degrees Fahrenheit. It averages about 40 degrees. The wind is also a factor. It blows almost continually with an average velocity of 10 to 15 miles per hour and has reached a velocity of 100 miles per hour. Another factor is the ice. It is 60 or more inches thick by late May. Snow commences to fall early in September. The maximum snowfall, 8 inches, is in October. The Arctic snow is fine and dry. It constantly migrates, causing drifts and sometimes poor visibility, which may stop or hamper operations. Fog, produced by open bodies of water, causes poor visibility. Still another element of extreme importance in Arctic construction is the ground. Let us look at it in cross-section. The surface ground, which may be silt, sand, gravel, or some mixture of these materials, freezes during the winter and thaws from 1 to 5 feet during the summer. The period of maximum thaw extends from mid-July through August. The part which freezes and thaws is called the active layer. Below this layer is permanently frozen ground, extending to depths of 900 feet and more in northern Alaska. This permanently frozen ground is called permafrost. Some unusual phenomena occur in the active layer. If there are local differences in the composition of the soil, insulating cover, and moisture content, differential freezing may occur. As a result, heaving may take place during freezing and settling during thawing. This differential freezing may have even more striking results if heavy cover prevents or retards freezing at any surface point. The active layer freezes from the top down, except at the one point. Any water between the frozen part of the active layer and the permafrost is under great hydrostatic pressure. This pressure causes the water to break through, with resultant icing on the surface. Sloughing and creeping of a mass of ground may also occur during thawing. This happens frequently when the moisture content of the active layer is high and the permafrost table slopes steeply, as on a hillside or near a riverbank. Most of these conditions have been carefully summarized in a work feasibility chart, which indicates what may be expected for each condition throughout the year. This chart is the basis for a schedule of operations. Excavating and earthwork can take place during July and August. Surveying can go on from April through October. Water supply must come from deep rivers and lakes, except between June and September. Let us first consider certain basic problems common to most construction in the Arctic. All supplies, except sand, gravel, and water, must be delivered by ship or by air. They must then be delivered to the construction site by tractor train or by bush plane. A second problem is construction personnel. Native workers are used wherever possible. Skilled specialists in construction must be recruited outside the reserve and carefully trained to work under Arctic conditions. At best, more man days and equipment days are necessary to do a job than for similar work in temperate climates. Selection of a suitable site or location for a facility is another of these problems. The site should be that which will permit the most efficient construction with the least possibility of permafrost troubles. It should also have good natural drainage, or should be easily drained by artificial means. High water marks should be carefully studied, especially if construction is to be undertaken in river bottom or old river areas. The peak runoff of water occurs at the time the river ice breaks up. Adequate drainage is thus necessary to keep facilities from being flooded. When the active layer of the ground is thawing, drainage is again important to keep operations from being bogged down. Often walkways must be constructed. Carefully located ditches provide artificial drainage when natural drainage is inadequate. The ditch should be lined with gravel to prevent erosion and sloughing, which could lower the permafrost table and damage any road, building, or other construction. A dependable water supply is another basic problem. The best source is a lake or river which does not freeze to the bottom. All drinking water is chlorinated before using. Filtering is recommended for large numbers of personnel. Water in quantity is transported in heated water wannigons. If water is pumped any distance, insulated pipe and heat transfer units are required. Water is necessary not only for construction purposes, but also for personnel and for drilling operations. An adequate supply of fuel is another problem in most construction projects. From the drums, the fuel is normally pumped into the red fuel wannigan. From the tank in the wannigan, the fuel is pumped into the storage tanks outside buildings. 55-gallon drums or 1,300-gallon pontoon sections are used for fuel supply tanks. Still another problem common to most construction projects is waste and sewage disposal. The barrels used as latrines must be removed regularly. Such waste, as well as garbage and debris, can be dumped in designated areas or on the ocean ice. Excavation, grading, and earthwork are other problems common to many construction projects. Most earthwork is done from mid-June to the 1st of September. During this period, all types of gravel, sand, and silt can be moved with conventional earth-moving equipment. When the ground is frozen, earthwork cannot be done so easily. Riverbed gravel can be secured through the ice, but the method is troublesome and the river may not be handy. Coarse sands and gravels located above the water table may be loosened by dynamiting or by shocking with a dozer blade or air hammer as early as May. But the earth to be moved or excavated is seldom above the water table. A limited amount of frozen earth can be thawed by steam produced by a small Alaska Prospector's type low-pressure boiler. The steam is forced into the ground through steam points. The thawed ground is little more than sludge and is readily removed in a sludge bucket. Such earth moving is inefficient. It is suitable only for a rush job in preparing a building foundation site, or, as we see here, in excavating a meat storage cellar in the permafrost, where the temperature remains from 16 to 20 degrees Fahrenheit throughout the year. The final problem common to most construction work in the Arctic is foundation construction. For example, a structure built on the active layer may change the frost table. After a thaw, settling is probable on the south side. After freezing, if moisture has been trapped, heaving is probable. A building with a piling foundation resting on the permafrost may lower the permafrost table. During thaws, settling may then occur. And during freezing, heaving may take place. If the building keeps the active layer from freezing, water may creep into the building with disastrous results. To take care of such possibilities, special methods of constructing foundations are necessary. Heavy foundations are placed on footing or piling, which extends well into the permafrost. Undue lowering of the permafrost table is prevented by wide spacing of piles, by leaving adequate ventilated space between floor and ground, and by insulating the floor. The heaving force of the active layer is counteracted by the add freezing force of permafrost to piling. If need be, the piling can be anchored in the permafrost. In other instances, the silt, mud, and organic material of the active layer must be removed, and the foundation placed either on the sand and gravel of the active layer or directly on the permafrost. The excavation is then backfilled with gravel to prevent floating and heaving. In such construction, care must be taken to avoid introducing water into the backfill and to avoid lowering the permafrost table. Road construction is limited to the camp area and immediate surroundings. The active layer is removed if it contains moisture holding material such as silt, fine sand, or organic matter. Such material is replaced by gravel, and drainage is provided. Airstrips are similarly constructed, except for the final surfacing. The barrow runway has a gravel foundation and a pierced plank landing surface. It has been successfully used by large 2- and 4-engine aircraft. The runway has held up well. The only maintenance has been the replacement of pieces of mat bent by rough landings or by construction equipment. The Barter Island runway was constructed on a gravel spit bordering the Arctic Ocean. The 5,000-foot runway was built in 3 days using only 2 bulldozers and 2 carryalls. Various types of buildings have been constructed. Most have been temporary structures of the advanced base type, Jamesways, Quonsets, and utility arch-ribbed structures. The Jamesway has a double floor with insulation between layers. The wooden framework is made of pre-cut arch ribs. This framework is covered rapidly with a heavy canvas backed with glass wool insulation. The completed huts may be placed on sleds to make mobile housing units, or they may be placed on gravel mats to furnish temporary housing. The Quonset, northern type, has a 20 by 56-foot foundation placed on a well-drained gravel mat. Holes for channel plates are made, and flooring is laid. Double flooring with insulation between layers is sometimes used. When the floor has been completed, the steel arch ribs are attached to the channel plates and braced by metal purlins and trimmers. When all arch ribs and the windows are properly in place, the entire interior is lined with insulation board. Metal splines are placed between horizontal joints and masonite strips over the rib joints. When the interior has been completely lined, blanket insulation is stretched over the insulation board and the steel corrugated sheets are nailed into place. The completed Quonsets, heated by 2 convection-type oil heaters, are used for living quarters, mess halls, stores, and dispensaries. The utility arch rib buildings are basically oversized Quonsets, 40 by 100 feet. This addition to the Barrow Administration Building was built during the winter. The ground was thawed using steam points and an Alaska Prospectors type boiler. Holes for mud pads were then dug. A 12 by 12 by 2 footing and a 6 by 6 post went into each hole. After setting footing first and then the post, the hole was refilled and tamped. The tamping was carefully checked by the foreman. Sills were then placed on the posts. Balloon or braced type framing was used. Diagonal sheathing increased the strength of the building. A gable roof was used and is recommended, although flat roofs have been used successfully on small buildings. Floors, sidewalls, and ceiling were well insulated. Derrick construction must take place wherever oil wells are drilled. Thus, a site with good drainage is selected. In some localities, adequate foundations on bedrock or thick native gravels are found. However, when necessary, the active layer is replaced with gravel to form a dependable pad. If this method is not possible, or if a large drilling rig is to be used, a foundation of piling extending well below the permafrost table, must be constructed. At Cape Simpson, where the piling method was used, the ground was first thawed and piling was placed in the permafrost. After the piling had been cut off, the foundation sills were put in place and leveled carefully and spiked to the piling. The drill cellar was then dug, again with the aid of steam points. To provide insulation, the pit was then lined on the sides with moss and celotex, and on the floor with concrete, tundra, and a second layer of concrete. The next steps at Simpson were usual ones in oil derrick construction. The rig floor was laid, the winch was placed, and the framework of the derrick went up step by step. The oil derrick was completely enclosed with insulating canvas. The construction of high steel towers illustrates in extreme form most of the problems faced in heavy construction work in the Arctic. At the site, an excavation has been made into the permafrost for the foundation pedestals. Digging held to a minimum has been done as early in the season as possible. Holes have been drilled into piles which have already been placed to carry the weight of the form. Over the piling, a layer of sand, a layer of rock wool, and another layer of sand have been placed to insulate the frozen ground from the mass concrete to be poured above. Reinforcing rods are placed in the footing and welded. The form is placed and concrete is poured. The concrete is carefully rotted. After the footing slab has set, the reinforcing rods for the pedestal are placed. The pedestal form is placed. The foundation bolts are leveled and centered. Again, concrete is poured. The concrete is a mixture of selected local beach sand and gravel and cement from the States. High-strength early cement is used so that the permafrost is disturbed as little as possible. Any water around the pedestal caused by the 90-degree heat of the hydrating concrete must be removed as produced, again to avoid disturbing the permafrost more than necessary. The excavation is backfilled so that normal thermal conditions in the ground are quickly restored. The base plate for each pedestal is prepared. Each base plate is then installed. With this job done, the foundation is completed. It is ready to carry the load of steel framework. All steel is laid out on the ground, checked, and bolted into sections to facilitate handling. A crawler-type crane raises the first members. When in position, they are bolted to the base. Member by member, the tower sections are raised and bolted into place. As the work proceeds at higher levels, the basket boom is used to raise tower sections. Thus, the tower moves toward completion. Many things can be built in the Arctic by men who know and understand the conditions and who adapt construction to those conditions instead of trying to fight them. The low-pressure boiler used by Alaska prospectors in the field is the chief unusual tool found in Pet 4. Only with such a source of steam could heavy construction work take place in permafrost regions. The men, too, are different. They must be hardy specimens, well-trained, well-clothed, and well-fed. Knowledge gained from experience, added to new knowledge of Arctic conditions, will be reflected in future construction in polar regions.